Okay, so now we gotten to exercise 3.2. So now we're supposed to write code that evaluate these expressions. Oops, there's a little thing here. And checks if they are either true or false. And we are supposed to sort of reason our way through it on paper and then try it out in code. But I think I'll skip that part a little bit and I'll just try to reason through it using Python. So I started the Python interpreter in the last exercise, and you can go back and revisit them to see how I started Python. So now I'm just going to press enter a couple of times to get like a fresh view here. Actually, let's just open this up like this. So in this case, we're supposed to evaluate the expression that 9 is greater than or equal to 3 times 3. So 3 times 3 we can write like this using the multiply sign. Then in order to compare 9 to this value, well, I use this operator. This is the greater than or equal operator. So in this case, it's going to evaluate to true because y is in fact equal to 3 times 3. No, sorry, not y. 9 is equal to 3 times 3. If I wanted to check if it was equal, I would do this. So what do you think happens if I put in 19 here? Well, it's still going to be true because 19 is greater than 3 times 3, which is equal to 9. Now we are supposed to check if 91 is not equal to 9 times 11. So 91, let's first check if it's equal to 9 times 11 like this. It's not, because this is actually going to be 99. So how can I check if it's not equal? Well, this is just where you need to know something, because to write that something is not equal, we can use the not equal operator. So the way we write the exclamation mark in this case is as not, and you just have to know this is how you make that comparison. So in this case, it's going to be evaluated to true because it is indeed true that 91 is not equal to 9 times 11, which is the same as asking this. That's of course true. And then we, of course, also can conclude that this must be false, because something cannot be different from something and equal to it at the same time. Now it gets a little bit more tricky. Either 2 is greater than 3 or 3 times 3 is not equal to 9. Wow. Okay, so let's just start with the first part. 2 is greater than 3. How would I write that? 2 is greater than 3, like this. It's false. Next part. 3 times 3 is not equal to 9. And now I use this not equal operator. Then I need to string them together. So I need to say either 2 or the other one. So how would I do that? I would need to write something like either this or 3 times 3. Like this. It doesn't matter if I include spaces or not between in the multiply operator. I'm just going to do it. Well, this is of course not going to work because it doesn't recognize either. However, if I remove either, it actually recognizes the OR operator. So the OR operator means that this expression is true if it's the case that this is true or this is true. So if either of them are true or both of them are true, this is going to evaluate to true. But in this case, this is false and this is false. So we actually end up in the one situation where it's equal to false. But if I change this a little bit, for instance, to this expression, it's going to evaluate to true. Because even though this is false, we are saying something false or this condition is met. And if this condition is indeed met, so the whole thing is going to evaluate to true. It'll actually have the form of false or true, which happens to be true. Okay, so let's move on. The cosine of 3 pi is a negative number. Well, in that case, we need to know how to write pi. So in order to write pi, I first import math, and then I can do math.pi. That was something we did in the last exercise. How can I do the cosine? Well, This turns out not to work. You can just check. It doesn't know what cos is. However, and again, something you just need to know, math, this package contains a lot of useful mathematical functions, including the cosine. So in fact, this is something we can evaluate. And then you can maybe remember from trigonometry in high school that this is indeed equal to -1. So now we can just multiply it by 3, and then we can sort of imagine a little clock that moves around or something like that, and we can check that it's equal to -1. In fact, for every odd number, this would be -1. 9 is greater than or equal to 5 and divisible by 3. Okay, so now it gets a little more tricky. So first let's try with the first condition. We already know how to do that. 9 is greater than or equal to 5. But how do we check if something is divisible by something else? So I'm not actually sure if there is a little bit of a hint on how to do it. Yeah, we can do that using this operator, the modulo operator. It's kind of a nasty way of doing it, but I guess it is discussed in the book, at least as far as I remember. It's a little bit since I read the book, sorry. But let's just try to check it. So we can say 9 modulo 3, and that's 0. Okay, so what does this actually mean? Well, this is actually the remainder by division. So what we can do is that we can observe that 9 can be written as 3 times 3 plus 0. So in this case, this 3 is the same 3 that I have here, and then the remainder is going to be 0. And this is, since I can write 9 like this, the remainder is what I get out of the modulo operator. Oh, sorry, this is of course a little bit of nonsense that I wrote here. But this is how that I can write 9. Okay, so let's try to do modulo 2. In that case, I would need to do something like this. And then Python internally figures out that the 9 can be represented like this. And since 9 can be represented as 4 times 2 plus 1, the modulus by 2 is equal to 1. Again, I get a syntax error. I don't know why I press enter. It's a little bit silly. What do you think happens if I do 9 modulo 1? Well, let's try to reason our way through it before we get to the result. So let's insert I can write 9 as, actually let's just use equality signs here. I can write that as 9 times 1 plus 0. So in that case, it would stand to reason that the modulus have to be 0. So let's try to do that. It's equal to 0. What happens if you do this? Well, this definition don't make sense anymore because, yeah, it's not defined. Python will complain. What about 9 modulo 5? Well, in this case, we need to observe that 9 can be written as, I'm writing that this is a common. 9 can be written as 1 times 5 plus 4. So in that case, the modulus is going to be 4. And it is. Okay, that was a really long story and I got a little bit sidetracked. But 9 is greater than or equal to 5, so now we know how to write it basically. We can look at a case where it's divisible by, that was where I got sidetracked, sorry. If I do the modulo, 9 modulo 3, we can observe that if the modulus is equal to 0, it must be divisible, because that basically means that I can write 9 as, in this case, 3 times 3 plus 0, and that means that it must be divisible by 3. So I can just check if the modulus is equal to 0, and then I know it's divisible. So if I check 9 divided by 3 is equal to 0, that's true because it's divisible, and now I can verify for other values. This is false. This is true because 1 divides 9, and this is in fact also true because 9 divides 9. Anyway, so I can use this, and then we basically just need to string it together with the first condition, 9 is greater than or equal to 5, and I can check that by saying greater than or equal to 5, and then it's both have to be true, so I need to write and. And this is how I can evaluate this expression. Except, of course, I need to change this to a 3. Okay, That problem was a little bit mean, I feel. The cosine of 3 pi is a positive number or it is equal to 0. So let me start by computing the cosine. Oops, I forgot to type math. Yeah, so you're probably also going to see this more than once. I know that I have, certainly. So let's check if this is a positive number. How do I do that? Well, I check if it is greater than or equal to 0. And I guess positive number means that it could potentially be 0. If it has to be strictly positive, I would write it like this. But we'll just do this. That's of course going to be false because it is -1. Or it is equal to 0. Well, I'm already checking if it's equal to 0. So this is actually solving the problem. I think what we have in mind is that we can also explicitly check if it's equal to 0. So we could also do it like this. It's still going to be false. But I think it is far nicer to just do the comparison in one go using the greater than or equal to 0 operation. Oh. Okay. Assign the value true or false to a variable y depending on x being greater than 10 and an even number. Okay, so let's try to define x as something. So let's say x is equal to 12. So how do we do that? First we need to check if x is equal. Well, this is actually the modulus operator again. So if I do x modulo 2, that means that x will be written as something times 2 plus the remainder. Well, if the remainder is 0, we know that 2 divides x. However, if the remainder is 1, 2 does not divide x. So let's check in this case. It should be 0, and it is, because x is equal to 6 times 2 plus 0. However, let's say that x is equal to, I don't know, 15. Then x modulo 2 is actually going to be, let's see, it's going to be 7 times 2 plus 1. So it's going to be equal to so in this case, it's going to evaluate to the 1, like this. Okay, so now we can use that to check if x is divisible by 2 or even by just saying x modulo 2 is equal to 0. That's only true if x is even. And we can check that that works for other values than 15 by, for instance, going up and trying with x equal to 12. And we'll see that it correctly says that's 2. Okay, let's try to solve it. X is greater than 10 and it's an even number. So we can say greater than 10. I guess that must be strictly greater and even. We can check that like this. And then we need to assign this value to a variable y, and we can do that like this. So in this case, y is going to be equal to what? True, right? And we can check that this works for other values. So let's say x is equal to 6. What's going to happen? Well, if x is equal to 6, this is going to be true and, no, sorry, this is going to be false and x divisible by 2 is equal to 0. That's going to be true. So it's going to have the form of false and true, and that's going to be evaluated to false actually, because with the AND operator, both have to be true at the same time. So we can just check that, and that is indeed true. On the other hand, if I said x is equal to 21, well, what's going to happen here is that this will be true, but this is going to be false, because the remainder modulo 0 of this is actually going to be 1, because 21 is equal to 2 times 10, or 10 times 2 to be completely consistent, plus 1. So this will evaluate to, false, like this. Okay, so this is moving a little bit slowly. I think I'll stop here and then try to do the next exercise.